It has exceptions to rules, right? We don't have sheeps and popcorns and fishes. We should. So yeah, it's just terrible. Plus the idea that you drive on a parkway and park on a driveway, right? That's my favorite out of everything. Driving on parkway and parking on driveway. And shipment and cargo, they're also really good, right? You put the shipment on a truck, right? And you put the cargo on a ship. Put the shipment on a ship and put the cargo on a truck and a car and then move it around, right?
The plural of mouse is mice, the plural of moose is mooses.
Yeah, I know. Oh, amazing,
Well,
right?
The root word for moose is from a Native American language, and it's after we already stole mouse from a different language, which had, in that language, had mice as the plural, or at least close to it. We never actually made the change afterwards.
Yeah, you know.
Because English has stolen everything from every other language. Like, we're not really based on anything. It's a bastardization of Latin languages, which are bastardizations of Latin and a bastardization of a German language, all like mixed in a blender.
Basically, yeah. You won't find that in math. Zero exceptions. Okay?
So,
There's a rule and you follow it. Yes.
Can you just, and a stupid question, but just fully explain exactly what dy or dx means? It just means the derivative of y with respect to x, right?
Yes, so we are looking for the change. So when I say dy dx, and this will be clearer later when we talk about change as a differential, but right now, if you are thinking about this, here's some kind of function. And you know this is your x axis, and this is your y axis. From this point to this point, you see this location from A to B changed for delta x, which is your dx. And then there is this change in height, which is delta y. So to go from this point to this point, if you want to call this t, right, and have dt, which is dt, some time had to pass, or you had to cover some distance. And then the height changed as well. So when I say dy dx, this actually means change of y divided by change in x, but over a very small time frame.
So it's the infinitely small slope.
Yes. No, it's a slope of the line
over infinitely small space.
Between 2 points, yes.
Okay.
So this space over here is infinitely small. So think about it taking a photograph. It takes in a split second. Now think about those really fast, large FPS cameras, right? That can shoot slow motion. That would take 10,000 pictures a second, right? Or 30,000 pictures a second. So you really can see something evolve. Like taking lightning. I'm not going to take time now to go on YouTube and show you the lightning shot with that camera, but it can be done. Yes.
The cameras, like when you look out, they were working on cameras with the shutter speed so fast that they could actually see around buildings. Like they could check the photons to see like what was reflecting back. And they could see like.
No, I did not know about that.
Completely different, but they managed to slow down light enough to be able to see light move.
That'd be awesome.
Okay. You can find a video on YouTube later.
I will.
It's not really visual entertaining. It just looks like a red spot that's bouncing. But
You have to start somewhere. I gotta check that out. That's really cool stuff. Back to taking the derivatives.
What's the difference between dy over dx and just d over dx?
Well,
I know it's the implicit and explicit difference, but what exactly?
Well, here it
does
is.
that mean?
We say y equals f of x. We're cool on that. So you can either write y equal x squared, or you can write f of x equal x squared. Pre-calculus. 100% clear, right?
Yeah.
Take the derivative. We can say, what is the derivative of x squared? Now, you know the answer is 2x. But I'm just saying, I could also write that as this. And then it's that. So what is the difference? This over here is the instruction. You know the instruction, license and registration, right? Here. So this is instruction which says take the derivative. This is the derivative. So you get to replace all of this here with 2x. So this will say the derivative is the derivative of this of your function. The derivative of, right, d times y, the derivative of x squared in respect to x is 2x. So the whole thing over here is the derivative. This is instruction. Take the derivative in respect to x of, again, times x squared. So notationally, this part, d dx, the d dx part is just the instruction what to do. Later on, we're going to have integral. It will be a squiggly line, and it will say take the integral of, and you will have function following it in respect to x, because there will be dx at the end. So both integration and derivative, the notation is instruction what to do. So when you say 3 plus 2, this is instruction that you are supposed to add. That's the instruction, right? So you will say 5. But I can also go and say take the derivative of 3, and you would say it's 0. So this is instruction that says what to do with function or a number. And then integration. Take the integral of 3 in respect to x, and you will get this. Now this is our chapter 4.9, and then chapter 5 and 6 and 7. They're all doing that. So, in Calc 2. So, we call these things mathematical operators. This is operation on the numbers, and these operators operate on functions. I can have 3x and 3 sine x and so on. Does it make sense? So the difference between the two is this is instruction, and then that's the answer.
The other question is, since we're adding dy over dx into our what we just learned, could we replace dy over dx with a constant, with a number or variable?
No, because you don't know what that y is.
So you can't, like, crazy on a circuit, you can't solve for y and then differentiate to find out what that is, correct?
Correct. That's why we have implicit differentiation. Because if we could solve for y, there would be no need for...
So it's basically another variable.
The entire dy dx is the chain part. This would be your dy dx. Because if you put this thing to by, then you will be taking the derivative of y to the 8th, which would be what? 8y to the 7 dy dx. You see that? This is your dy dx, because that was y and that was the derivative of that. Maybe I should write that as well in notes. Yes?
Wait, I'm sorry. So why is the first part of the derivative not part of the dy dx?
First.
Meaning, why isn't 8 times d to the dx over x plus 1 over 7 part of the dy dx?
Because that's the function that you're taking derivative of. And then the rest is the chain.
Oh,
if it's more...
I get it. Because y itself is always considered a function.
Of x.
Because y is always a function of x. You're taking almost like an invisible function, because you can't figure that out when it's implicit.
You don't know what it is, yes.
You don't know what it is. So the dy dx is like a stand-in for the function that you don't know.
Yes. But now I'm going to actually show you exactly what you discovered, which is great. But you can't do this efficiently every time. Observe this. X squared plus y squared is equal to 9. I can solve this for y and get this. That's that magical thing that we didn't know, but we didn't care because we didn't have to.
So
It was simply 2x plus 2y dy dx. And what was dy dx? Dy dx was the derivative of this. That derivative. The derivative of whatever that thing was equals 0. And it will all work out, actually. The problem is that plus minus over there and, you know, certain things.
does every dy dx have a plus minus in it?
No, some actually can't be done at all. What are you going to do here? You can't even fish it out. You fish this one out, which means you are applying inverse sine, you trap this one. This is why we haven't done any of the complicated problems yet. We only took the cheapest one, which is sine, circle, and did that one. And we are lucky that we can kind of massage it a little bit to get at least some glimpse of what the function would be.
So since dy dx is a stand-in for something we usually can't find, how does it help? Well, what do we do with that?
Well, that is what you're looking for. That's why we don't worry about it, because the dy dx is what you want, because that is the derivative.
We can still find out what it's equal to, even though we have no idea what it is itself. Okay.
And that will equal to whatever mess you have. In this case was negative x over y, or y over x. What was it? Negative x over y, right? Which will produce the slopes. Note that I still don't know what this is, but when I'm looking at the point 3, 4, that's the 3, that's the 4. I plug them in, and it's 3/4,
really
negative 3/4.
Roundabout way of finding dy dxy, because of the fact that the y is like attached to the x.
Y is the consequence of x, so x
Yeah.
is the independent variable, y is dependent variable. Great questions. Awesome.
So, can we use implicit differentiation to solve for, say, like sections of a non-function?
Well, that's what it's for. It's to find the derivative technically of anything. You see, I'm going to now write y equals, let's go with 5 cosine x. Okay, that's it. And I'm going to use implicit differentiation on this because I can. So if I take the derivative of this in respect to x, look what happens on the left. I get dy dx, and then there is equal sign, negative 5 sine x dx dx, but they cancel. I did not have to use implicit differentiation at all. This was a vanilla problem. We just use our basic derivatives to solve this problem. But we can also use the sledgehammer, right? So implicit differentiation is literally like a sledgehammer. You can put the painting, you know, the nail for the painting in a wall carefully, right, using the sledgehammer. And you can also break the concrete walkway with a sledgehammer. The little hammer that you can use to put the nail, right, in the wall, you can't use to break the concrete sidewalk. So implicit differentiation is this really strong, massive tool that you can use all the time. We don't actually use it when we don't have to, because simple problems can be done using the simple ideas that we established before. Great? All right. So now here is some of the, you know, let's do a few examples, actually, not just one, but few. So say we have xy plus 3 sine y is equal to 2x squared plus 8. We can fire up the software and ask software to graph this, and we will get the curve in the plane, which will do whatever the hell it does, okay? The fact is that that curve will still have tangent lines everywhere, which means there was the derivative, right, which means we should be able to find it. So let's see. I'm going to apply the derivative. I'm going to say, put the instruction in front, take the derivative in respect to x, and then we're going to go down through the calculation. Now, first term, what do we do?
Product rule.
Product rule. We have two functions multiplying each other. X is a linear function, and y is some unknown function. So x times y, product rule. The rest are vanilla functions. All right, so here we go. X times 1 dy dx. Do we all understand that the derivative of y is 1 times dy dx? Plus, copy y times the derivative of x is 1, and we are finally done with product rule. Then we have the plus from the problem, which I'm going to link with the red. So we know the first two terms are product rule, then we have the plus. What's the derivative of 3 sine y? 3 cosine y dy dx. Perfect.
And the dy dx is right next to the y or outside of the...
Outside of the cosine. It's a times, like a chain rule. It's a chain rule. Equals, right-hand side, 4x. Awesome. We are supposed to get dy dx alone. How do we achieve that? Factoring. Very good. So we are going to factor dy dx from the two terms that have it, get x plus 3 cosine y in parentheses, and then ship the y term to the other side because that one does not have, right, this term here, that term did not have dy dx, so I am shipping it to the right by subtracting y on both sides. And now what do you need to do to get dy dx alone? Divide by the parenthesis. Very good. Now, guys, you are looking at this problem. Might be complicated, might be crystal clear and easy. I don't know where you are right now, individually. But you have to understand that this thing over here produces slopes of the tangent line. This thing is the first step of the problem which says, find the equation of the tangent line at the point blah blah. Because what is implicit differentiation? It's just another way to find the derivative. Never lose the sights of the goal of the class. Find the derivative which gives you slopes, which gives you tangent lines. This is just a method. So this is not something that you are learning to know how to do a section. This is actually a first step of the most important problem, which is find the tangent line, y equal mx plus b. To find that m, sometimes you have to do this. Sometimes you have to just take the derivative of x squared. Sometimes you have to do quotient rule. All of the things that we learn in chapter 3 are shortcuts and procedures to find the derivative. The goal of the class is to find the tangent line. So consider this as a shortcut to some far more horrible procedure to figure this derivative if you don't have this. Limit, h goes to 0, right? Exactly. Measures the instantaneous change. You look at the speed and you know how fast you're going. You push the gas pedal, you know that if you push it halfway, you will accelerate at this rate. If you push it all the way, you should floor it, right? So the derivative measures that kind of instantaneous change. Right. For most part in life, you don't really care, but you observe it all the time. As simple as pouring milk into a glass, the height changes instantly. How fast it grows depends on how much of a tilt you put on the container of milk. Right. So the derivative measures how fast the level of the milk in the glass goes up. or how fast you drink it, right? So derivative measures change, and that's what we need. And it measures change in an instant, not over a long period of time. It's that instantaneous change that you can immediately, like the difference is between, let's say, I don't know, I want something ridiculous that is not math. Here, punching someone in the face and falling in love with someone. Falling in love with someone is average rate of change. It takes long time and usually leads to punch in the face. The punch in the face is instantaneous. Someone gets you in the face, and go pump, right? So that's pretty much how it goes. So the derivative versus the average. Average is over time, takes long time. Instant is that impulse. That's what's called instantaneous. And instantaneous, the difference between taking a video, taking a photo, you can take a 10-minute long video, shutter speed for a photo, right? That's what it is. Yes?
So that's the m in a y equals mx plus b equation.
This over here, yes. If you produce me with, I don't know, 3,7, let's say 3,7 is on this line, then I plug in 3,7, this becomes m, which we are actually going to do. The last example will be the full-blown example. We just have to do few of these because of the annoyance of fishing out the derivative.
Would you be able to give like a real world example when you prefer to have the tangent line as opposed to the slope?
Well, slope is the part of the tangent line. Tangent line will show you the direction on which, let's say, in a curve like this, and the car right there, and then the leaves and oil and stuff. If the car is to slid, the tangent line to this curve, which goes like this, is which way the car is going to go. So that's what it is. It's going to go off the road this way, because that's the tangent line. That's the velocity to this type of the position function. That's the real deal.
Right, no, it's just sort of struggling to think of like where you would actually.
And the answer is everywhere in engineering.
I took physics, and this is like, I think physics makes this a lot more understandable if you see like the real applications of it in physics.
Yes, because all of the physics is from derivatives.
It's literally acceleration.
Differential equations.
You can't find anything in physics without the acceleration.
Yes. We'll actually have a section on that. All right, let's take a look at a few problems that the author of the book thinks you guys should know. So these are not going to be as bad, right? Or they are, I don't know. We'll do 3 examples from the textbook, then we'll do the tangent line and we're done. So example number 1 from textbook, let's say number 8, says y squared plus 3x equals 8. And they also ask you actually to compute the slope at 1√5. Nice. So find slope m at, so literally 17 seconds for this. That's all you get. 17 seconds. 13 seconds left. All right, 17 seconds is up. The derivative of y squared is? So 2y dy dx, okay, plus equal, awesome. Subtract 3, divide by 2. So dy dx, we do all of that in one step, is calculus. And now to find m, negative 3 over 2 root 5. Rationalize it because you must. And that's the slope. Now please look at the screen. As soon as you plug in the number, the derivative changes notation into slope. As soon as you plug it in. So in the same step, you have to change dy dx into m, because remember, dy dx is the function that generates all slopes. As soon as you say this is the particular slope I want, you change that general dy dx for all slopes into the slope m for that point. Bueno? So they happen in the same step. You plug in a value root 5 here, immediately this changes into m for slope. And you can see that here, done. So that's the derivative, that's the value, and then all of it work together. Great. Two more examples, and then example for tangent line. The next example is root x, number 10. Root x minus 2 root y equals 0. And they want you to compute this at 4, 1. I hope you all have 1/4. Yes? No? Who cares? So we kind of memorized already that the derivative of root x is 1 over 2 root x. The derivative of y is 1 over 2 root y, and then 2 is cancelled. dy dx. Fish out dy dx, and then plug in 4 and 1. Get 1/4. All right, and then the spicy example from the textbook. Tangent xy equals to x plus y at 0, 0. So this will be considered tricky, but you got this. Mm-hmm. X times y, yeah. I can put parentheses if they don't have parentheses in the textbook. Yeah. So what do we do for the tangent part? What is it? It's a chain rule. And then what? And then the product for the inside. Nice. It's going to be terrible to fish out dy dx. But you know what? This thing over here actually simplifies life. Let me show you how. Yeah, we don't actually have to fish out dy dx. But let me. So the derivative of tangent, you said, someone? Secant squared of xy. Nice. And then we multiply by the derivative of the inside, which is copy the first, derivative of the second, right? Derivative of y is 1 dy dx, plus copy y, and then derivative of x is 1, equals to 1 plus dy dx, right? Now, in general, what would you do? You would distribute, and then you would put all of the dy dx terms on the left and non-dy dx on terms on the right. But you know what? They're looking for m. And they gave you 0, 0. So why not plug it right away? So you get your secant squared of 0, open parentheses 0 times m plus 0, equals to 1 plus m. Secant of 0 is 1 times 0 is 1 plus m, and m is negative 1, and you're done. This is how awesome math is on Saturday morning, or any other morning, or evening, or after lunch, immediately, yes. Math is awesome every time, except if someone shakes you out of bed, like, I don't know, say you passed out at 2:30 and someone goes at 4:15. So you lie. You lie. Can you take this derivative? Yeah. Instantaneous, right? You immediately explain the difference between instantaneous and average. All right, so the derivative, I hope, is understood, because we took the derivative of tangent. We have the product within the chain. So we take the derivative of the outer function tangent, which is secant squared, following the same dots, and then the derivative of that in the chain is the product rule between two functions. Y is the function of x. So when I take copy the first, derivative of y is 1, followed by dy dx, plus copy the second, derivative of x is 1, so y times 1, equal to derivative of x is 1, and derivative of y is 1 dy dx, just dy dx. And the trick now is, I don't want to go through algebra for no reason. Look at that, plug everything in. That's going to be a 0. Secant is 1 over cosine. Cosine of 0 is 1, so 1 over 1 is 1. So that's 1. And then 0 times, right, x is 0, y is 0. So 0 plus 0 is 0. 1 times 0 is 0. Move 1, and there we go. And at this point, I say, yeah, we could have done it here immediately. We haven't, but you could have just went 1 over 2 root 4 minus 1 over root 1m equals 0, m equals a quarter, and be done. That's fine. Depending on question is asking. If the question asks what is the derivative, you have to grind through algebra to fish out dy dx alone. And then once you have that, then you go and deal with the rest. Awesome. Let's just do one where it says find the equation of the tangent line. So let's finally see the entire problem. Here is the problem. This one is from the textbook. The graph is given to us so that we can see what kind of a change we are looking for. This is problem 28. It says x cubed plus y cubed is equal to 2xy. We want the tangent line at 1, 1. I will give you the graph, even though it's not necessary, but it's cool to know it. Clearly not a function. Clearly has a tangent line right there. That's what we are looking for. Instantaneous change at 1, 1, which is the slope of that red line. Find the derivative, plug 1, 1, get m, then you have m, and 1, 1 to find b, y to y equals x plus b, and you have your equation.
Really?
Yeah.
More or less. How about we schedule calculus for every day so you can relax? Like this.
Sounds very good.
Be at peace.
They make shit, yeah.
I don't know. I'll just figure out. See where that is.
Remember the trick, don't fish out for dy dx, just plug in 1, 1 across the board and drive through. Trying to basic algebra. I'm sorry? Did it explode? It's streaming. Says it's live and one person is watching.
One guy that religiously watches your streams, every single one.
Yeah.
All right, so let's see. We have 3x squared plus 3y squared dy dx equals to product rule 2x dy dx plus 2y, right?
Yeah.
Awesome. I am not going to, oh, actually, let me just, so I have the issue with the pen, so let me just restart the software. Okay. Is still issue? Still issue. Interesting. Okay. So what do I get now? I plug in 1 everywhere. For every x and every y, I plug in 1. So I get 3 times 1 plus 3m is equal to 2m plus 2. Magic. M is clearly negative 1, right? Just by looking at it. Green? Unleash y equal mx plus b. We have y is 1, m is negative 1, x is 1, b is b. So how much is b? So what's the equation of the tangent line? Put on a cloud. I like it on a cloud. This is the tangent line at 1, 1. For the same function, would tangent line change if I looked at, let's say, different point, 2, 2, or whatever is on the line? Nice. It's not a function.
And you can find the tangent line of that one if you wanted to. If you want to.
Yeah. But the tangent line would be different. However, the equation we have is not a function. Awesome. How can we make this extremely annoying? Like this. What's the third implicit derivative of something? You get the idea. So let's spend about 30 minutes to work out the second derivative, and then if you have a few hours at home, you do the third one. Just kidding. So higher order. Implicit derivatives. What is the second derivative of the circle? So find the second derivative, which is d squared y over dx squared for circle, and then we have, let's say, x squared plus y squared equals to 9, because we are going to recycle what we did before. We already established that the first derivative dy dx is negative x over y. Well, take another one. Take another derivative here. So as I put in front another derivative, please look at the screen. Does this notation make sense now? The notation in a peanut? Why is it d square y dx square? Why not dy square over dx square or something like that?
Because there's only one y.
Exactly. You are taking the derivative of one y at a time. So
That's the instruction of the D1.
take the derivative. It's instruction twice, right? Of what? Of the same function. First derivative will change it, but then you hit it again with the same instruction. Give me the license registration, you give the license, you give the registration, and then you give me the insurance. Fine, right? So, see, d times d is d squared, and then dx times dx is dx squared. Just for the notation, so we are notation like clean.
Dx squared just be in parentheses, right? Well, because dx would be in parentheses, the entire thing is squared.
Yeah, but notationally we don't do that. Cool. So we are taking another derivative at this point. It's like taking the first derivative now we already have. So we have that the d squared y over dx squared is equal to the quotient on the other side. We have the y squared, and then we have the y times negative 1 minus negative x times dy dx. Look at that. Your second derivative is in terms of the first derivative. You got to simplify. You got to plug that mess in if you are to compute further. So what's the second derivative? The second derivative now is going to be negative 1 plus x times dy dx divided by y squared. But this thing over here is negative x over y. Plug in. So it is negative y. Look. See? That's clearly negative y. We can go further if you need. Every pixel of that y?
If we zoom in more, it gets more pixels.
Yes. Until it looks like this, right?
Yeah, it's the entire zoom and the y.
Yes. All right. I would say thank you, but I'm not a nice person, so no. Negative y minus x squared over y divided by y squared, and we will multiply everywhere by y to eliminate double fractions, so times y on top, times y on the bottom, and we get that the second derivative is equal to negative y squared minus x squared divided by y cubed. What do we do for the third derivative now? Just do it again, and then plug in again for dy dx when it pops up. Not if, but when, and so on. So the seventh derivative is the first derivative of the sixth derivative, and you keep pushing and substituting dy dx and clearing the algebra, which ends section on implicit differentiation. Yes, I was about to say improper intervals. All right, bye stream. We will restart this after the break for the next section.